Okay, a little bit of a review. We've got a spot here to sketch the parent functions. So let's sketch what each of these looks like just in general, okay? So y'all know what a linear function looks like. It doesn't matter really what you graph on your paper, but the easiest thing, right, is just to graph y equals x. That's the easiest linear function to talk about. Makes a line, all right? We use the linear regression if our scatter plot looks like a straight line. Quadratic, the parent function would be x squared. That's a parabola that faces upward, that touches the origin. A cubic function, y equals x cubed, looks like this. Okay, we've gone over all these functions. These kind of basic pictures should be popping into your head. Quartic, it looks kind of like your quadratic, but usually what happens is it looks kind of like a W instead of just a U. That would be x to the fourth. Quartic is fourth degree. And then our new ones are exponential. Okay, like I wrote on the board, that could be something like 3 to the x, or it could be e to the x. Those are exponential. And then logarithmic, this is what your logarithmic parent function looks like. It could be log base 2 of x, or in the calculator, it always uses the natural log of x when you do the LN regression, the natural log regression. So, to figure out which model is best, we can look at the scatter plots, but there's a tool in your calculator that will tell us even more exactly, and we don't have to worry about looking at the scatter plot, fixing our window, and then deciding which shape looks best. In the box there, it says to determine the best model, we use what we call the correlation coefficient, and that is this variable r. The closer r is to -1 or +1, the better the fit. Okay, so the closer to -1 or +1, the better the fit. Closer to 0, that means it's not a very good model. Okay, but you have to make sure your diagnostics are turned on in your calculator. So right now, I need everybody to take their calculator. And if you know of an easier way to get to this, please let me know. But this is the only way that I know how to turn on the diagnostic. If you press second 0, it takes you to the catalog. The catalog has a list of every single command that is in your calculator. We're looking for diagnostic. Now, you don't need to just start scrolling down to the D's. You can skip there by pressing the X to the -1 button, the inverse button, beside the sign button, because there's a little D above that. It'll skip you down to the D's, and then you just scroll down to where it says diagnostic on, and you press enter, and then you press enter again, and it'll say done. So now, when we do a regression, there's going to be some more numbers that pop up on our screen. So let's look at an example of doing that. Number 5 here says the table below shows the operating cost in thousands of dollars of a small business from 2000 to 2005. Which model would fit this data best? Quadratic, quartic, or logarithmic? So it gives us 3 options. Since logarithmic is one of our options, we do not want to put a t equals 0 in there because it will not calculate it if we do t equals 0. So let's say that 2000 we'll say is year 10, okay? Just to give ourselves a starting point. So we'll do 10, 11, 12, 13, 14, and 15. So we'll put this data in, and we're going to be smart about this, and not everybody is going to type in or try to find each model. We're going to use our resources in our group here. So make sure everybody's got the data. Those texting fingers are good for something, right? I hear y'all typing. All right, so here's what I want you to do. There are only 3 models to choose from, and most groups have 4. So I need y'all to split it up. One person needs to find the quadratic regression, one person needs to find the quartic, one person needs to find the logarithmic, and then the extra person just pick whichever one you think may be it. Okay, take a guess and do that one as well. Okay, decide who's doing what. Okay, so I'm going to try a quadratic regression personally, because when I look at the data, I'm going to kind of maybe rule out logarithmic. I may be wrong in doing that, but my data seems to be increasing a little bit faster as we go on. Logarithmic typically slows down. So I'm going to try quadratic. So I do the quadratic regression. Let's see here. Let's not worry about, we're not going to put it in the graph, okay? We're not going to put it in the graph. So I'm just going to do the quadratic regression. So now, instead of just having A, B, and C, now all of a sudden I have an R squared. Okay? I have an R squared on mine. If you do the logarithmic, you should have an R squared and an R. So, based on your results, who has the closest R or R squared to 1? Which one? Quartic? Quadratic or logarithmic? Which one's closest to 1? Quartic? Okay, so this one's 0.969. So it's really easy to just do all these. 0.969. Quartic, we gotta scroll down. Okay, quartic is 0.999. That's really good. And then what is logarithmic? Okay, logarithmic is only 0.925. So yes, a quartic is the best model for this one. Okay, quartic is the best model. So let's use that model to predict or estimate here. I like to round to 3 places after the decimal. So here's our model. Y equals 0.023 x to the 4th minus 1.095 x cubed. And here's why I really like to put it in the graph, because I don't have to write all this stuff down. X squared minus 154.015x plus 453.95. Whew, what a model, right? It's a long one because it's 4th degree, so we go all the way from power of 4 down to a constant. So if we're estimating the operating cost in 2008, what are we going to plug into our equation? What do we plug in for 2008? Not everybody wants that. 18, okay? Because if 2000 was 10, then 2008, we just keep counting. We're going to plug 18 into our equation here. So I'm just going to put it into the calculator. I don't want to rewrite it with 18 replaced with all the x's. This one takes a little bit of time, doesn't it? Alrighty, so it says that the cost in 2018 is approximately, not what I wanted to do right there, 41.6. Well, the table rounded to the 10th, so we'll round to the 10th. 41.7, and this is in thousands of dollars. Oh, technology. There we go. Don't forget, it's a real world problem. We always put units on it. So put your dollar sign on there, and then you need to write 1,000 after that, because it's not just $41.70, okay? It's $41,000 here. Okay, let's do another one. Let's look at number 6. We're comparing our models here, seeing which one has the best fit. This time we've got a savings account. Which one fits best, linear, cubic, or exponential? Oh, okay. I'm going to do 9, 10. That's how I'm going to put it in. 9, 10, 11, 12, 13, and 14. Oh, okay, I'm hearing several people say it's definitely exponential. Let's look at these R values. For the linear regression, not too bad, 0.998, pretty good. Cubic, 0.998. Ooh, that's really, really close to 1 there for that R squared. And let's look at exponential. Does exponential give us exactly 1? Ooh, those are close. Really close. So does this one have more 9s than the other one? I didn't really pay attention. Yep, got just like 1 more 9. Okay, so exponential is the winner, which is a relief for me because we don't have to write down as much. Here's our model, 250.128 times 1.07. Oh, that rounds up, 1.08. 1.08. Oh, forgot my exponent, x. All right, now let's look at what the question is actually asking us. Estimate the year the balance will reach 1,500. So, what do? We'll plug it in, send it equal. Okay, now, we can graph it, or we just spent a couple days on solving these things. We set it equal. Can we solve this equation here without graphing? Can we solve it algebraically? What do we do first? Divide. Okay, we've got to get this exponential by itself. So we divide first by the 250, 1,500 divided by 250.128. Then what do? What did we do at this point to get the variable by itself? It's stuck in that exponent. How do we get it out of the exponent? Log form. Log, the base is always the same as the base of the exponential. And the whole point of this is the variable, we want it by itself. So the x goes on the right side of the number, the 5.997 goes inside. And how do we evaluate that number right there? Change of base, right? The log of 5.999 divided by the log of 1.08. So we get approximately 23.27 for x. And what did we do? We did 9, 10, 11, 12, 13, 14. So that means it's that many years since 2000. So the year would be sometime in the year 2023. Sometime in the year 2023. So you can do it this way. You can graph it. I think graphing takes a little bit more time because you have to adjust the window and wait for the calculator to graph it and then find the intersection and all that stuff. I think it's a lot faster to just do it algebraically here. But you can do it either way.